Welcome to the Deep Dive, the show that extracts the most important nuggets of knowledge from the latest research and big ideas.
Great to be here.
Today, we're plunging into something pretty exciting in the world of large language models, LLMs.
Mm-hmm.
We've all seen how powerful they can be, right?
Yeah.
Especially when they use Retrieval-Augmented Generation, RE, to pull in outside knowledge. The answers can be incredibly detailed.
Absolutely. RA is a game changer for making LLMs more factual and, well, knowledgeable.
But, and there's often a but. You know that feeling when you ask something complex and the AI response just takes that a little bit too long?
Oh, yeah. That pause.
Or maybe you're deep into a conversation and it feels like the AI suddenly forgets something you mentioned way back at the start.
Exactly. It loses the thread sometimes. That hesitation or that memory lapse in a long chat that really points to a core challenge we're facing.
That's what we're diving into today. You mentioned that pause, that bottleneck. What's actually happening under the hood there? Why do LLMs struggle when we give them a lot of information?
Well, it really boils down to a fundamental trade-off. The more context these long context inputs, you feed an LLM hoping for richer answers.
Which makes sense. You want it to have all the facts.
Right, but the more you give it, the more it struggles. We're talking about system latency, that lag. We're talking about huge memory demands for something called the key value cache.
The key value cache, that's like the LLM's short-term memory for the prompt itself.
Sort of, yeah. It stores intermediate computations about the input, and it grows really fast with longer prompts, and all this leads to lower throughput, basically, how much it can process overall.
So it's not just slow, it actually gets overloaded.
Precisely. And it's not a minor thing. The time to first token, TTFT, that wait before it even starts typing its answer.
Yeah.
That can increase quadratically with the prompt length.
Quadratically.
Yeah. And the time for each next word, the time to iterative token, or TTIT, that grows linearly. It's a huge barrier to making these things fast and practical, at scale.
Okay, so the internal processing is the snag. It's not just about throwing more computer power at it, which leads to the big question, doesn't it? How do we let LLMs use all this vast external knowledge efficiently? How do they access everything quickly without getting totally bogged down? Can we have our cake and eat it too?
That's the million-dollar question, or maybe $1 billion now. And it's exactly what this really groundbreaking new framework called REFRAG is trying to solve.
REFRAG.
Yeah, it just came out this month. It's from researchers at Meta Superintelligence Labs, the National University of Singapore, and Rice University. Really smart group.
And it specifically targets this RAG processing issue.
Exactly. It completely rethinks how LLMs should handle information and resetups.
All right. So our mission for this deep dive then is to give you, our listener, a clear shortcut to understanding REFRAG.
We want to show you how it promises to speed up LLMs dramatically.
Letting you tap into much bigger contexts, get lightning-fast answers, and really open up some new doors for what AI can do.
Let's get into it.
Okay, let's start by really digging into that core problem, this hidden information overload in RAG.
Right.
So when a standard LLM gets a long RAG prompt, maybe the original question, plus a bunch of retrieved documents, it has to process everything, right? Every single token.
Yeah, it allocates memory and compute for all of it.
Yeah.
Even if maybe half the documents aren't that relevant, or they repeat the same information.
I like your analogy earlier, the research assistant who reads every single word of 10 articles, even the redundant parts, before answering.
Exactly. It's thorough, but incredibly inefficient. And this points to something REFRAG cleverly exploits. RAG contexts often have what the paper calls sparse information.
Sparse information,
Meaning that different retrieved passages, while maybe broadly related, often don't have super high semantic similarity. They might cover different aspects, different details. They aren't like one single tightly written essay.
Okay, so they're related, but kind of distinct chunks.
Precisely. And this leads to what the researchers identify as block diagonal attention patterns.
Okay, block diagonal attention patterns. That sounds technical. Break that down for us. What does that mean for efficiency?
It sounds complex, but the implication is pretty straightforward. It means that when the LLM calculates attention, figuring out how much each word should pay attention to every other word, a lot of the calculations between these distinct retrieved passages are actually, well, kind of unnecessary.
Ah, so it's spending time comparing words in passage A intensely with words in passage B, even if they cover slightly different things.
Exactly. Back at the assistant analogy.
Okay.
It's like meticulously comparing every sentence in a history book with every sentence in a science book, just because they were both pulled up for the same broad query. It's overkill.
And you mentioned the retrieval system already does some ranking, right? It finds the most relevant stuff first.
It does. But a lot of that useful ranking information gets effectively thrown away when the LLM just treats the whole context dump as one big sequence and starts crunching everything. It's working way harder than it needs to.
Okay, that makes total sense. It's overprocessing because it doesn't recognize the inherent structure of the RAG input. So how does REFRAG fix this inefficiency?
This is where REFRAG gets really clever with its solution. You can think of it as a three-step process: compress, sense, and expand.
Compress, sense, expand.
The core idea is pretty elegant. REFRAG basically says, look, most of the heavy computation over this retrieved RAG context during the answer generation phase, it's not strictly necessary.
We can get rid of it.
We can remove a lot of it with minimal, often zero impact on the final answer's quality.
All right, so step one, compress. What's happening there?
Instead of feeding the LLM decoder all the raw text, all the tokens from those retrieved passages.
Which we know is computationally expensive.
Right. REFRAG uses pre-computed compressed chunk embeddings.
Embeddings, like numerical representations, but compressed.
Exactly. Think of them as highly efficient, compact summaries of the key information within chunks of the text.
Okay, so you feed the LLM these summaries instead of the full text.
Well, partially, but the advantages are huge. First, it dramatically shortens the effective input length for the decoder, less stuff to process directly.
Makes sense.
Second, you can often reuse these pre-computed embeddings, saving redundant work if the same chunk appears again.
Ah, efficiency gains there, too.
And crucially, it changes the complexity of the attention mechanism. Instead of scaling quadratically with the number of tokens, which can be tens or hundreds of thousands, it now scales quadratically with the number of chunks, which is far, far smaller. That's a massive computational saving.
Wow, okay. That alone sounds like a big deal. But then there's sense and expand. What does that add?
This is where it gets really dynamic and intelligent. REFRAG uses a lightweight reinforcement learning policy, RL policy.
Reinforcement learning, like training an AI through rewards.
Exactly. This RL policy acts like a smart editor, or maybe a gatekeeper. It looks at the compressed chunks and selectively decides which ones are so important that they need to be fully expanded back into their original token form for the decoder to see in full detail, and which ones can just stay as those low-cost compressed embeddings.
So it's making a judgment call on the fly about what information needs the high-resolution treatment.
Precisely. And a really key part of this is what they call compress anywhere.
Compress anywhere.
Yeah, unlike some older methods that could maybe only compress the very beginning of a document, REFRAG can apply this compression and selective expansion at any point in the input sequence.
Why is that so important?
Think about multi-turn conversations. New information comes in with each turn. Or complex tasks where an AI agent needs to refer back to different pieces of information gathered over time. Being able to compress flexibly within the sequence is vital for those kinds of applications.
Okay, you can't just top off the beginning. That makes sense. And you're saying REFRAG does all this without messing with the core LLM itself. Like, you don't need a special version of Llama.
Exactly. That's a huge plus. It doesn't modify the base LLM architecture or add new parameters to the main decoder. It's an optimization framework built around the existing LLM.
So it's like adding a really smart preprocessor and manager.
That's a good way to think about it. An intelligent layer that optimizes the information flow before it hits the main LLM decoder.
Let's try to visualize it. Say I ask, who is the president of USA? And RAG pulls up, I don't know, 10 news articles.
Okay.
REFRAG's encoder first breaks those articles down into chunks and creates those compressed embeddings, those summaries.
Right. Step one, compress.
Then this RL policy, the smart editor, looks at the chunks and says, okay, these 2 chunks directly mention the current president. Let's expand those fully. These other 8 mention related political context. We can probably just use the compressed summaries for those.
Exactly. That's the sense and expand part. It identifies the critical bits.
And then this optimized mix, a few full detail chunks, many compressed summaries, gets fed to the standard Llama decoder.
Which can now process it much, much faster because the input is effectively shorter and the attention calculations are simpler.
And it outputs the answer, Donald Trump is the president of the United States, much quicker than if it had to wade through all 10 articles word by word.
That's the core idea. Efficiency through intelligent selection and compression.
Okay, that's clever. But how does REFRAG learn to be that smart? How does it train that encoder and that RL policy?
Good question. The training process has a few key stages. It starts with something called continual pre-training, or CPT.
CPT.
Yeah, this is basically an initial alignment phase. You take a lightweight encoder, the part that does the compressing, and the main LLM decoder, and you train them together a bit. Often the task is simple, like predicting the next paragraph in a document. It just gets them used to working together.
So they learn to speak the same language, effectively.
Kind of, yeah. Establishes a baseline understanding, then comes a really critical step. Yeah. The reconstruction task.
Reconstruction task? What's that about?
This is where the system learns to make good compressed embeddings. The encoder compresses a chunk of text, and then it has to project that compressed embedding into a format the decoder can understand. The decoder's job, using only that projected embedding and maybe some context, is to try and reconstruct the original text.
Ah, so it forces the encoder to create summaries that don't lose crucial information.
Exactly. It teaches the encoder to compress, effectively minimizing information loss. And it also teaches the system how to translate between the compressed world and the token world. Initially, during this phase, the main decoder is often kept frozen. Its weights aren't updated.
Why freeze the decoder?
The focus is purely on training the encoder and its projection layer.
But reconstructing lots of text from just a few compressed summaries sounds hard.
It is. It's a challenging task. That's why REFRAG uses curriculum learning.
Like starting with easy lessons and getting harder.
Precisely. It starts with simpler reconstruction tasks, maybe reconstructing just one chunk from its embedding. Then it gradually increases the difficulty reconstructing 2 chunks, then 4, and so on. This step-by-step approach is really essential for robust training. It lets the model build up its capabilities gradually.
Makes sense. Build a foundation first, and then the final piece is the reinforcement learning part for the selective compression.
Exactly. That RL policy, the smart editor, needs to learn which chunks are the most valuable to expand. It's trained using rewards.
And the reward is based on
It uses a negative perplexity score as the reward signal.
negative perplexity.
Okay, perplexity is basically how surprised the model is by the next word,
Right.
right? Lower perplexity is better, means it's predicting well.
That's right. So by rewarding the policy for actions, compressing or expanding chunks that lead to lower perplexity, better predictions from the main decoder, the policy learns to identify and prioritize the information that's most essential for generating an accurate answer. So it learns, expanding this chunk really helps the decoder get the answer right. Let's reward that decision.
You got it. And there's a fascinating finding here in the research.
Yeah.
They found that REFRAG, using this smart RL-based selective compression, can actually achieve lower perplexity than a model that just compresses everything uniformly at a relatively low compression rate.
Wait, so being selective is better than just compressing everything a little bit?
Apparently, yes, because the selective approach intelligently keeps the most critical information in full detail, even if other parts are heavily compressed. It really shows the power of adaptive, context-aware compression. It's not just about shrinking things. It's about shrinking the right things.
That is fascinating. Okay, so we have this clever framework, train through these stages. What's the payoff? What does this mean in terms of actual performance numbers?
The numbers are pretty staggering, honestly. REFRAG achieves an average 30.85 times acceleration in time to first token, TTFT.
30 times faster for the first word to appear.
30.8, 5 times faster. Yeah. Which is also 3.75 times better than the previous state-of-the-art method they compared against, something called CEPE.
Wow, and this is without hurting the quality of the answers.
That's the crucial part. They report achieving this speedup with no loss in perplexity or accuracy. Same quality answers, just way, way faster.
That's huge. What about context size? You mentioned it struggles with long inputs.
REFRAG massively helps here too. Because it's so much more efficient, it allows LLMs to effectively handle context sizes 16 times larger than they could before.
16 times. So you can feed it vastly more information.
Vastly more, yeah. Think about the implications for complex research or analyzing huge data sets.
Okay, these numbers are seriously impressive. But sometimes these benchmarks are under ideal conditions. Are there specific types of ROG situations where REFRAG might maybe not be quite as beneficial or where its advantages are less pronounced?
That's a fair question.
Hmm.
REFRAG's biggest advantage comes from exploiting that sparse information structure we talked about.
Right, the block diagonal attention.
Exactly. So if you had a hypothetical RG scenario where the retrieved documents were incredibly dense and interconnected, almost like a single, perfectly coherent text, well, the gains from selective compression might be smaller. The RL policy would likely decide to expand almost everything anyway.
Because everything is crucial in that case.
Potentially, yeah. But honestly, most real-world RGAG applications, where you're pulling from diverse web pages, internal documents, databases,
Yeah.
they tend to have that scarcity. Information is often repeated, or passages cover distinct subtopics. That's where REFRAG really shines.
So for typical, messy, real-world ARG, it's likely to provide significant benefits.
Very likely, yes. It's really engineered for that common scenario.
Okay, that makes sense. So let's talk about how this specialized approach really reinvents RGAG itself. You mentioned strong and weak retrievers.
Right. So RAG systems rely on a retriever to find relevant passages first. Sometimes the retriever's really good. A strong retriever finds exactly the right stuff.
Yeah.
In those cases, REFRAG matches the accuracy of a standard llama model using that perfectly retrieved information. But, and this is key, it does so with a 5.26 times speed up in TTFT.
Same quality answer, 5 times faster. Nice.
Very nice. But now, consider the weak retriever scenario. This is arguably more common in the real world. The retriever finds generally relevant stuff, but maybe it's not perfectly precise. Maybe there's some noise, some less useful passages mixed in.
The messy reality.
The messy reality. Here's where it gets really interesting for you, the listener. In these weak retriever cases, REFRAG actually outperforms standard llama in terms of answer quality.
It's better. Why?
Because its much larger effective context window, that 16x expansion we mentioned, allows it to sift through more of that messy, weakly relevant information and still find the useful nuggets. Llama, with its limited context, might miss them.
Ah, so it can handle more hay to find the needle.
That's a great way to put it. And here's another kicker. If you compare them at equal latency you give REFRAG enough time to process, say, 8 retrieved passages, which might be the same amount of time Llama needs for just one passage.
Yeah.
REFRAG consistently achieves better performance, about 1.22% better with strong retrievers and 1.93% better with weak retrievers, on average across the benchmarks they used.
So for the same amount of waiting time, you actually get a deeper, more informed answer with REFRAG because it could process more context.
Exactly. More depth for the same weight. That's a fantastic trade-off for the user.
That really changes the game. What about conversations? You mentioned it struggles with losing the thread.
REFRAG addresses that head-on too. Because standard LLMs have fixed context windows, long conversations inevitably lead to truncation. Old information gets chopped off.
Right, it forgets at the beginning.
Yeah. But REFRAG's compression allows it to effectively keep much more of the history alive within its working memory. It can maintain robust performance across many conversational turns, handling multiple passages of context from the ongoing discussion without hitting that hard limit nearly as quickly. The flow is preserved.
So much longer, more coherent conversations are possible.
Definitely. It feels much less like talking to something with severe short-term memory loss.
And this extends to other long input tasks, like summarizing big documents.
Yes, absolutely. The paper shows REFRAG achieving state-of-the-art or significantly better performance compared to baseline models when summarizing lengthy articles, like academic papers from ArcSev or medical text from PubMed.
And it does this quickly.
While keeping the latency low, yes. It demonstrates it can really grasp and distill complex information from very long inputs efficiently.
Okay, so summing up its advantages,
Yep.
what really makes REFRAG stand out in this, very crowded field of LLM optimizations?
Well, I think a few things are key. First, it's specialization for RAG. It's not just a general long context solution. It's tailored for the specific sparse structure often found in RAG.
Right, it understands the nature of the input.
Second, that compress anywhere capability. That flexibility is huge for dynamic interactions like conversations or agentic workflows, where information isn't just tacked onto the beginning. Some older methods couldn't handle that. They'd break the causal flow or were limited to prefix compression.
That versatility seems critical.
Third, it hits that sweet spot of efficiency and accuracy. Massive speedups, lower memory use, but without sacrificing the quality of the output. And crucially, you don't need to retrain your base LLM from scratch, which is a massive undertaking.
Making it much more practical to adopt.
Hugely practical. And finally, there's future potential. The paper mentions it's complementary to other prompt compression techniques.
Oh, so you could potentially layer these methods.
Potentially, yes. You might be able to use refrag and another compression technique on top, potentially squeezing out even more efficiency. The research is still ongoing, but it suggests refrag is a powerful component in a broader toolkit for optimizing LLMs.
Okay, let's recap this deep dive then.
Yeah.
We've really unpacked REFRAG. It's this powerful new framework that seems to fundamentally change how LLMs handle lots of information, especially in these RAG setups.
Yeah, by using this compress, sense, and expand strategy, intelligently compressing chunks, using RL to sense which ones need full detail, and expanding only those critical parts.
The results are pretty stunning. Massive speedups, like over 30x faster time to first token, the ability to handle 16 times more context.
And importantly, boosting accuracy, especially in those common weak retriever scenarios, all while maintaining performance across diverse tasks like Q&A, long conversations, and document summarization.
So for you, our listener, what this really signals is a future where the AI applications you use are not just smarter and more knowledgeable thanks to RAG.
But also dramatically faster and way more responsive. Imagine asking a complex question that requires synthesizing info from dozens or hundreds of sources and getting a thoughtful answer almost instantly.
Or having an AI assistant that can follow a really complex project discussion over weeks, never forgetting key details mentioned early on.
Exactly. It starts to break down those frustrating barriers of latency and limited context that we currently experience. It paves the way for much more seamless and powerful AI interactions.
It really is incredible to think about the downstream effects.
Yeah.
Which brings us to our final thought. If LLMs can now be effectively taught to discern, prioritize, and manage information at the scale, to essentially scale their intelligence without getting overwhelmed, what kind of completely new frontiers does this open up? Think about something like truly personalized learning, an AI tutor that can instantly draw on vast educational resources tailored perfectly to your learning style and progress without any lag.
Or real-time scientific discovery. Imagine researchers being able to feed massive, live experimental data streams into an LLM enhanced with refrag, having it identify patterns or suggest hypotheses on the fly, sifting through noise in a way humans just can't manage at speed.
When you remove these fundamental bottlenecks of speed and context, what becomes possible? It really does make you think, doesn't it?
It certainly does. The pace of innovation is just relentless.
Thank you for joining us on the deep dive. We hope you feel a little more informed about refrag and maybe a lot more excited about where AI is headed next.